Now, example 2.3. Figures A and B show the field lines of a positive and negative point charge respectively. This figure shows the field lines of positive negative charges, and in this field the points P, Q, A and B are represented. Now question A. Give the signs of the potential difference Vp minus Vq, Vb minus Va. B. Give the sign of the potential energy difference of a small negative charge between the points Q and P, A and B. C. Give the sign of the work done by the field in moving a small positive charge from Q to P. D. Give the sign of the work done by the external agency in moving a small negative charge from B to A. E. Does the kinetic energy of a small negative charge increase or decrease in going from B to A? Now see, the field lines given to you for positive negative charge. In field lines of positive charge, we can see point P and Q, and in the field of negative charge, point A and B. Now first question. Give the sign of potential difference Vp minus Vq, Vb minus Va. Now we know this thing. For a point charge, the electric potential, that is V equal to Kq by R. So V proportional to 1 upon R. So here P is at less distance compared to Q. So potential at P, that will be more than potential at Q. Vp is greater than Vq. So Vp minus Vq is positive. Here A is at less distance, B is at more distance. So we can say B will be less negative than A. So we can write Vb minus Va here, that is positive because Vb is less negative, so we can say it is greater than A. Okay. Now B. Give the sign of the potential energy difference of a small negative charge between the points Q and P and A and B. Now potential energy of small negative charge at point P, that is UP equal to minus QVP, at Q, UQ, that is minus QVQ. Now Vp is greater than Vq, so when we multiply it by minus Q, then it will be opposite. So here UQ will be greater than now UP, so UQ minus UP is positive. Similarly, if we multiply potential at A and B with small negative charge, then UA, that is equal to QVA, UB, that is QVB, and now here see UA will be greater than UB because A is closer to negative charge, so UA minus UB, that is positive. Then see, give the sign of the work done by the field in moving a small positive charge from Q to P. So work done from Q to P, that is given by VQ minus Vp. So here say Vp minus Vq is positive, so we can say Vq minus Vp will be negative, so work done is negative. Clear? Then in moving a small negative charge from B to A, work has to be done by the external agency. So WB to A, that is VB minus VA, as per previous it will be positive. Then does the kinetic energy of a small negative charge increases or decreases in going from B to A? So when small negative charge is moved from B to A, due to repulsive force of this source negative charge, its velocity decreases. When its velocity decreases, then we can say its kinetic energy that will be also decreases in going from B to A. Clear to all of you? Now next topic, that is equipotential surfaces. Equipotential surface, that is a surface with constant potential at all the points on the surface. Now to understand this particular concept, let's consider a point charge. Now taking that particular point charge, imagine a spherical cell having radius equal to r. Now if we consider this particular point at the surface of this spherical cell, then the potential will be kq by r. But if you consider this particular point, then here also the potential will be same kq by r because distance is r. Here also you will get the potential that is kq by r. It implies that on this particular spherical surface, at each and every point the potential will be same one. So here we can say now for a point charge, the equipotential surfaces will be spherical one as shown in this particular figure. Now here we have to prove one more thing. Actually, for equipotential surface at each and every point, the electric field that is perpendicular to the surface. Now that we can prove here. See how. Now we know this thing. If in the given electric field a unit positive charge is moved from point A to point B, then the work done against the field, that is minus integration A to B E dot dr, and that gives you the potential difference between those two particular points. Now here see, if we consider infinitesimal small displacement only up to dr, right? 2 points which are situated at distance dr from each other, then between those 2 points the potential difference that we can write minus E dot dr. So that is minus E dr cos theta. But this potential difference between those 2 points on the given equipotential surface, that is 0, because on the equipotential surface at each and every point the potential that is same one. So if we take delta V that is equal to 0, electric field is not 0, dr is not 0, means cos theta is 0, so theta is 90, which is the angle between E and dr. Now displacement that is on the equipotential surface. So we can say at each and every point on the equipotential surface, electric field that is perpendicular to the surface. Now if we think about the uniform electric field as shown in the figure. Suppose you take electric field in the x direction, then its equipotential surfaces will be parallel to the yz plane. Clear? So perpendicular to the field. Clear to all of you? Now for dipole, the equipotential surfaces will be as shown in this figure, and for two identical charges, the equipotential surface will be as shown in this particular figure. Clear to all of you? Now next topic, that is relation between field and potential. Say here, suppose we consider two equipotential surfaces close to each other having potentials V and V plus delta V. So here delta V, that is the potential difference, or we can say change in V in the direction of electric field. Here delta L, that is the perpendicular distance between these two equipotential surfaces. Now imagine a point P on surface B. Now suppose the unit positive charge is moved from point P to surface A against the field. Clear? So in this particular case, the work done, that is E into delta L. Here delta L, that is the distance between these two surfaces. So we can write this work done, that is the potential difference between these two surfaces. So as per that, E delta L, that is the potential difference between these two, that is when it is moved from B to A, so potential difference is VA minus VB. Potential on A, that is V, on B, that is V plus delta V. So we can write V minus V plus delta V. So it will be minus delta V. So here we can write E, that is equal to minus delta V by delta L. If you take only magnitude wise the relationship, then you can write E, that is minus delta V by delta L, that is delta V upon delta L simply. If electric field, that is uniform one, then simply you can write here the relationship, that is E, that is equal to V by D. Okay, and here this relationship that we can use to solve many problems and MCQs, right? Now here we take this particular relationship. Now we can write the relationship like this also. E equal to dV by dr, and in vector form you can take E vector, that is dV by dr. Now in this particular case you have to take partial differentiation, because R, that is the function of x, y, z. Okay. Now that we will discuss what is the partial differentiation and how it is carried out. So here we can write this particular equation as E, that is equal to, now if we take the vector form, then we have to consider the negative sign also. So minus del V by del x I caret plus del V by del y j cap plus del V by del z k cap. Okay, and this is the partial derivative. Clear? Now later on we will discuss how this one is carried out. But here very important thing that you can observe, that is with the help of a scalar quantity, the potential, you can find the vector quantity. You can find the vector quantity. Now from this particular relationship you can conclude for these 2 points. Say here, one, that is electric field is always in the direction in which the potential decrease is steepest one, means maximum decrease in the potential takes place always in the direction of electric field. And second, that is, suppose here we consider this particular displacement, that is unit, then if the magnitude, its magnitude means the magnitude of the electric field that is given by the change in magnitude of potential per unit displacement normal to the equipotential surface. So perpendicular to this equipotential surface, if we take the unit displacement, then per that unit displacement, whatever is the potential difference, that will give you the magnitude of electric field. Clear to all of you? Now see, in the previous theory we discussed this thing, the relationship between electric field and electric potential. If the electric field that is uniform one, then simply we can write E that is equal to V by D or V by R simply. Okay. But in the electric field, if at different positions the potential is continuously changing one. Okay. And it depends on suppose X, Y, Z, and the field that is also changing in that particular manner. Then how we can find the electric field at a particular point? So in that particular case, we have to consider the partial derivative. So now let's take one simple example related to it. This example is not given to you in the text, but for understanding we are taking this one. See, in a certain region, the electric potential that is given by the formula V, that is a function of x, y, z, 2x square y plus 3y cube z minus 4z 4x. Find the components of electric field and the vector electric field at point 1, 1, 1 in this particular field. Okay. So, see here. Now, V that is function of x, y, z and that is given to you, and the point where you want to find the field that is 1, 1, 1. Now we have to take first components. So if you differentiate this V with respect to x, then it will give you x component of electric field. When you differentiate V with respect to y, it will give you y component of electric field. And when you differentiate V with respect to Z, then it will give you Z component of electric field. Now let's see. Ex that is del V by del x. So we can write that is del by del x of V. Substitute the value of V here. Now differentiate it. So for x square the differentiation is 2x. So first term that is 4xy. In second term there is no x. So it is constant term. So differentiation with respect to x will be 0. Here differentiation of x is 1. So that is minus 4z4. Then after substitute the value of x here, because we want this particular component at this point. So here x is 1. So substitute the value of x is 1, y is 1 and z is 1. Okay. So you will get 0. Then after Ey that is equal to minus del V by del y. Differentiate with respect to y. So now substitute value of V. Differentiation of this first term. Here differentiation of y that is 1. So first term 2x square. Differentiation of this one y cube that is 3y square. So 3 into 3 9, 9y square z. Here there is no y, means this will be treated as constant term. So its differentiation is 0. Now substitute here value of x, y, z. This coordinates 1, 1, 1. So you will get 2 into 1 square plus 9 into 1 square 1 equal to 11. Then Ez equal to minus del V by del Z. So that is equal to del by del Z of V. Differentiate this one. So here in first term there is no Z. So it will be treated as constant term. Differentiation will be 0. For Z it is 1. So differentiation is 3y cube. Then minus differentiation of z raised to 4, that is 4z cube. 4 into 4 16. So minus 16 z cube x. Now substitute x, y, z, that is 1, 1, 1. So you will get minus 13. Now E that is 11 j minus 13 k caret, right? But here we have the relationship E that is minus del V by del Z. So resultantly you can write this is equal to minus 11 j plus 13 k caret. Or see, directly you can apply negative sign here also. If you take Ex equal to minus del V by del X, then no need to write here in this manner. But first here we calculated as per magnitude only. So now finally we have to represent as per the relationship E equal to minus del V by del X I caret plus del V by del Y j caret plus del V by del Z k caret as per that. Now apply one negative sign here, so your final result will be like this. So here see, with the help of scalar quantity, you will obtain the vector quantity. Clear to all of you? Now the next topic, that is potential energy of a system of charges. Suppose we think about a system of charges as shown in the figure. Now we have to calculate the total work done for the assembly of this particular system. And we know this thing, that total work done will be stored in it in the form of potential energy. So for this particular assembly, first we think about charge Q1. Suppose charge Q1 is brought from infinity to point 1 having position vector R1. But when we bring charge Q1, at that time there is no any other charge. So we can say there is no electric field. So when there is no electric field, then work done to bring this charge Q1 from infinity to point 1, that work done, that is equal to 0. So charge Q1 is placed at point 1 having position vector R1. In this, the work done, that is 0. Now when charge Q1 is placed at position 1, then due to charge Q1, the electrostatic potential at any point P, that is given by V1 equal to 1 upon 4 pi epsilon 0 Q1 upon R1P, where R1P, that is the distance between 1 and point P. Okay. Now next, suppose we bring charge Q2 from infinity to point 2 having position vector R2. So here the total work done, that is charge Q2 into potential of charge Q1. So we can write the work done in that process, that is 1 upon 4 pi epsilon 0 Q1 Q2 upon R12, where R12, that is the distance between point 1 and 2. Clear? Now this total work done to prepare the assembly of these two charges Q1 and Q2, that will be stored in it in the form of potential energy. So we can say this thing, the potential energy of a system of two charges Q1 and Q2, that is given by U equal to 1 upon 4 pi epsilon 0 Q1 Q2 upon R12. Similarly, now we can calculate the potential energy of a system of three charges. Okay. Now suppose here, if we think about any third point where we want to place charge Q3, then at that particular point there will be the potential of charge Q1 as well as potential of charge Q2. So the potential of Q1 at Q3, that is 1 upon 4 pi epsilon 0 Q1 upon R13. Similarly, potential of charge Q2 at 3, that is 1 upon 4 pi epsilon 0 Q2 upon R23. So we can say the resultant potential at point 3 due to charge Q1 and charge Q2, that is V12 equal to 1 upon 4 pi epsilon 0 into Q1 upon R13 plus Q2 upon R23. Now if we bring charge Q3 from infinity to this particular point 3, then the total work done, that is Q3 into the potential at that particular point. So we can write W3, that is Q3 into potential due to 1 and 2 at point 3 having position vector R3. So we can write 1 upon 4 pi epsilon 0 Q1 Q3 upon R13 plus Q2 Q3 upon R23. And now this total work done to assemble the system of 3 charges that will be stored in it in the form of potential energy. So here the total work done in assembling the system of 3 charges, that is W1 plus W2 plus W3. W1 that is 0. So 0, then W2 that we calculated 1 upon 4 pi epsilon 0 Q1 Q2 upon R12 plus W3 that is this one 1 upon 4 pi epsilon 0 Q1 Q3 upon R13 plus Q2 Q3 upon R23. So here the resultant work done to assemble the system of 3 charges which is stored in the form of potential energy. So we can say now the potential energy of a system of 3 charges Q1, Q2 and Q3, that is U equal to 1 upon 4 pi epsilon 0, that is taken common here. So Q1 Q2 upon R12 plus Q1 Q3 upon R13 plus Q2 Q3 upon R23. So here this total work done that does not depends on the path. It depends only on the positions of the charges in the assembly. Clear? So in general for n charges we can write the equation for a potential energy of the system of n charges, that is 1 upon 4 pi epsilon 0 sigma I equal to 1 to n and I is less than j that is also up to n. So Qi Qj upon Qij, or we can write that is k sigma I equal to 1 I less than j to n Qi Qj upon Qi, here we have to write Rij actually, so rectify it. Now example 2.4. 4 charges are arranged at the corners of a square ABCD of side D as shown in the figure. Question A. Find the work required to put together this arrangement. B. A charge Q0 is brought to the center E of the square, the 4 charges being held fixed at its corners. How much extra work is needed to do this? So again here, as discussed in the previous theory, if you want to calculate the work required to put together this arrangement, then first of all we have to bring charge plus Q at point A, and then after at point B, C and D we have to bring charge minus Q plus Q and minus Q respectively from infinity, and in this process we have to calculate the total work done. Now suppose first we think about the work done in bringing charge plus Q from infinity to point A. So when we bring charge plus Q at A, at that time there is no any other charge, there is no electric field. So in this particular process the work done that is equal to 0. Okay. Then after second stage, now we have to bring charge minus Q from infinity to point B. But at that time plus Q at A is present. So in that particular case the work done that is potential at point B into charge minus Q. Now, work needed to be done, that is charge at B into electrostatic potential at B due to charge plus Q at A. So we can write minus Q into potential of plus Q, that is Q upon 4 pi epsilon 0, and this particular distance is given to you D in the question. So we can write upon D. So this is equal to minus Q square upon 4 pi epsilon 0 D. Now third. Now we have to calculate the total work done in bringing charge plus Q from infinity to point C. So here total work done to bring charge plus Q at C, that is equal to charge plus Q into potential at C due to charge at A, means plus Q, and charge at B, that is minus Q. So charge Q at C into potential at D due to charges at A and B. Now charge at C, that is plus Q, and potential of A at C, that is 1 upon 4 pi epsilon 0, Q upon distance between A and C, that is diagonal, so root 2 D, plus potential of minus Q at C, that is minus Q upon 4 pi epsilon 0 D. So we can write that is equal to, now if we take this Q common, then equal to minus Q square into 4 pi epsilon 0 D minus 1 upon root 2 plus 1. Here minus Q is taken common, so here it is written minus 1 by root 2. Now we have to calculate the work done to bring charge minus Q from infinity to point D. So again we can write that work done is charge at D into potential at D due to charges at A, B and C. So we can write now charge at D into potential at D due to charges A, B and C. So charge at D, that is minus Q, potential at D due to A, that is plus Q upon 4 pi epsilon 0 D, due to B, that is minus Q upon 4 pi epsilon 0 D root 2, then due to C, that is plus Q upon 4 pi epsilon 0 D. So we can write here, if we take Q common, then minus Q square upon 4 pi epsilon 0 D 2 minus 1 upon root 2. So total work done to assemble the system of these 4 charges, that is the summation of all the work done. So we can write here minus Q square upon 4 pi epsilon 0 D common. In first case the work done was 0. In second case it was minus Q square upon 4 pi epsilon 0 D. Then plus 1 upon root 2. Then plus 2 minus 1 upon root 2. If we simplify this one, then our answer will be minus Q square upon 4 pi epsilon 0 D into 4 minus root 2. Now see here, the work done depends only on the arrangement of the charges and not how they are assembled, right? So we can say this thing as per definition. This total work done, that is the total electrostatic potential energy stored in this particular system of charges. Now see here, one important thing. Here we solve this problem as per the theory, right? So as per theory, what we did here? We brought one by one charges from infinity to a specific point, and then we calculated the work done in that particular process. But see, in the previous theory, we discuss this thing. The potential energy of a system of two charges that is given by U equal to K Q1 Q2 upon R12, right? But suppose we have a system of four charges. So when we have a system of four charges, 1, 2, 3, 4, four charges suppose we have, then here directly we can solve this problem. In MCQ, you can do this thing. You have to consider the possible number of pairs here. See how? First we take the pair that is 1, 2, then 1, 3, then 1, 4, then after we take the pair 2, 3, then 2, 4, and then 3, 4. Clear? So here now for each pair, if we take the potential energy as per this equation. So here for 1, 2 we can write Q1 Q2 upon R12. For 1, 3 Q1 Q3 upon R13. Then for 1, 4 Q1 Q4 upon R14. Then for this one Q2 Q3 upon R23. Then Q2 Q4 upon R24. Then Q3 Q4 upon R34. And then after substitute these distances and you will get the resultant potential energy, right? So in very short you can solve the problem. Clear to all of you? Now next topic, that is potential energy in an external field. So potential energy of a single charge in an external field. Now in the external field, suppose at any particular point a charge Q is placed, then its potential energy at that point, that is charge Q into potential at that particular point. Clear? Because now electric field is already present. So if electric field is present, so at any point in that electric field, definitely electric potential will be there. So here potential energy of Q at position R in the external field, that is Q into potential V at R. So here see, when charge Q, suppose we take that is equal to E, that is charge of electron. So here if electron E is placed at any point in the electric field, then we can say its potential energy, that is E into V. Now here if we take the potential difference between 2 points, then the total work done, which is the energy stored in the electron to move it from point 1 to point 2, having potential difference equal to 1 volt. Then we can say if charge Q, that is E, is accelerated by the potential difference of 1 volt, then the energy gained by it, that is Q into delta V. So that Q into delta V, that is 1.6 into 10 raised to minus 19 into 1, that much joule. And this particular energy, that is called 1 electron volt energy. So 1 electron volt energy, that is 1.6 into 10 raised to minus 19 joule. Clear? And here this unit electron volt, that is most commonly used in atomic and nuclear and particle physics. Now the next in this one is potential energy of a system of two charges in an external field. So when we take the potential energy of two charges in the external field, right, then we have to take first charge Q1 at position R1, that is potential energy will be Q1 into V at R1. Then we bring the another charge Q2 at position R2. Then at position R2, due to electric field itself, potential is there. But due to charge Q1, potential is also there. Right? So, for charge Q2, if we place it at position R2 in the external electric field E, then the total work done, that is Q2 into V at R2 as well as Q1 Q2 upon 4 pi epsilon 0 R12, because there is a potential of charge Q1 also. So when we prepare an assembly of two charges Q1 and Q2 in external field, then the total work done, that is equal to Q1 into VR1, Q2 into V at R2 plus Q1 Q2 upon 4 pi epsilon 0 R12. So we can say here the total work done, that is the total potential energy stored in that particular assembly, right? So Q1 V at R1 plus Q2 V at R2 plus Q1 Q2 upon 4 pi epsilon 0 R12, where R12, that is the distance between 1 and 2. Clear to all of you? Now example 2.5. A. Determine the electrostatic potential energy of a system consisting of two charges 7 microcoulomb and minus 2 microcoulomb, and with no external field, placed at minus 9 centimeter 0 0 and 9 centimeter 0 0 respectively. B. How much work is required to separate the two charges infinitely away from each other? C. Suppose that the system of charges is now placed in an external field E equal to A into 1 upon R square, where A, that is 9 into 10 raised to 5 coulomb per meter square. What would be the electrostatic energy of the configuration? Clear? Now, solution. First, we have to find the electrostatic potential energy of a system of these two charges, and these two charges are placed at these 2 points. So, we have the equation for the potential energy of a system of two charges, and that is 1 upon 4 pi epsilon 0 or K Q1 Q2 upon R square. Sorry, R. Right? Now, here Q1, that is 7 microcoulomb, so that is 7 into 10 raised to minus 6 coulomb. Q2, that is minus 2 microcoulomb, so that is minus 2 into 10 raised to minus 6 coulomb. Now distance between those two charges R12. So one charge is at minus 9 centimeter and another one is at plus 9 centimeter. It implies that the distance between those two charges, that is 9 plus 9, that is 18 centimeter. So that is 0.18 meter. Now if we substitute all these values here, then K, that is, or 1 upon 4 pi epsilon 0, that is 9 into 10 raised to 9. Then 7 into 10 raised to minus 6 minus 2 into 10 raised to minus 6. So directly we can write 7 into minus 2 into 10 raised to minus 12. Divided by 0.18, your answer turns to minus 0.7 joule. Now second question here. How much work is required to separate the two charges infinitely away from each other? Now see here. If we separate these two charges infinitely away from each other, then for that work done, that is the change in potential energy. Now, change in potential energy, that is U final minus U initial. U final means U2, initial means U1. So U2 minus U1. Now when these two charges are separated by infinite distance, then as per this equation you can understand if this distance is infinite, then the potential energy will be 0. So U2 that is 0 and U1. So at this particular position we already calculated. So minus 0.7. So 0 minus 0.7. So your answer that is 0.7 joule. Then third question. Now the system of charges is placed in the external field. And now what is the electrostatic energy of the configuration that we have to calculate? Now the potential energy due to the interaction between two charges, this 1 upon 4 pi epsilon 0 q1 q2 upon r12, that will remain as it is. But in addition to that, two more potential energies will be there. One that is due to interaction of charge q1 with electric field, and another one that is interaction of charge q2 with electric field. Clear? Now, to find out the potential energy of q1 in the given electric field at a particular point, we have to find the potential at that point, because potential energy that is q into v. Now here relationship E, that is A into 1 upon r square, that is given to you. Now we already derived the relationship between electric field and potential, that is E equal to minus dV by dr. So dV that is minus E dr. Now E that is 1 upon r square into A. So we can write V that is integration minus E dr. E is replaced by A upon r square, and if you integrate 1 upon r square, then that is minus 1 upon r. A is constant, so keep it as it is. So finally you will get V that is equal to A by r. Now the net electrostatic energy of the configuration in the external field, that is Q1 into V at position R1 plus Q2 into V at position R2 plus Q1 Q2 upon 4 pi epsilon 0 R1 2. Now both the charges are placed at 9 centimeter from the origin. So we can write A upon R1 for VR1 into Q1. Then for VR2, A upon R2 into Q2 plus Q1 Q2 upon 4 pi epsilon 0 R. Now substitute the values. So A that is 9 into 10 raised to 5. Q1 7 into 10 raised to minus 6. 9 centimeter, so 9 into 10 raised to minus 2 meter. Plus again A 9 into 10 raised to 5, Q2 that is minus 2 into 10 raised to minus 6. Again distance R2 that is 9 centimeter, so 9 into 10 raised to minus 2. And this Q1 Q2 upon 4 pi epsilon 0 that we already calculated here. So substitute directly minus 0.7. And now if we solve this one, our answer will turn to 49.3 joule. Clear to all of you? Now next topic, that is potential energy of a dipole in an external field. Suppose we have a dipole with charges Q1 equal to plus Q and Q2 equal to minus Q, separated by distance 2a, which one is placed in the external electric field E, an electric field that is uniform one. Now when electric field is uniform one, then the net force acting on the dipole, that will be equal to 0, but some torque will act on it, and when the dipole is placed in the uniform electric field, in the previous chapter we studied this thing, the torque acts on it, that is tau equal to P cross E, where P that is the dipole moment. Now here the work done to rotate the dipole from angle theta 0 to angle theta 1 with infinitesimal small angular speed with no angular acceleration, that is given by W equal to integration theta 0 to theta 1, and it is rotated from theta 0 to theta 1 with so many infinitesimal small displacements d theta, d theta, d theta, like that. So the total work done, that is tau external d theta and integration of it from theta 0 to theta 1. Now tau, that is Pe sin theta. Now integration of sin theta, P and E, that is constant. So integration of sin theta, that is minus cos theta. And if we substitute the limits, then we can write Pe cos theta 0 minus cos theta 1. Now here, if we consider this particular total work done on the dipole, then we know this thing that will be stored in the form of potential energy. So here if we take theta 0, that is pi by 2. So that is a special case we can consider here. So this will be 0. And from theta 0 equal to pi by 2, if it is rotated by theta, then we can take theta 1, that is theta, cos pi by 2, that is 0. So our potential energy, that turns to minus Pe cos theta. So we can write minus P dot E. So in uniform external field, when the dipole is placed at some angle theta, then we can say its potential energy, that is minus P dot E. Clear to all of you? Now next example 2.6. A molecule of a substance has a permanent electric dipole moment of magnitude 10 into 10 raised to minus 29 coulomb meter. A mole of this substance is polarized at low temperature by applying a strong electrostatic field of magnitude 10 raised to 6 volt per meter. The direction of the field is suddenly changed by an angle of 60 degree. Estimate the heat released by the substance in aligning its dipole along the new direction of the field. For simplicity, assume 100% polarization of the sample. Now see here, it is given to you the molecular dipole moment, that is 10 raised to minus 29 coulomb meter. So dipole moment of each molecule is this much. Okay. Now here a substance has this much dipole moment. A mole of this substance is polarized. We know this thing. In one mole, how many molecules are there? So that is equal to Avogadro's number, that is 1 mole has a 6 into 10 raised to 23 number of molecules. Now one molecule have this much dipole moment. So this much number of molecules have total how much dipole moment. So we can write the total dipole moments of 1 mole molecules, that is 6 into 10 raised to 23 into 10 raised to 29. So that is 6 into 10 raised to minus 6 coulomb meter. Now the direction of the field is suddenly changed by an angle of 60 degree, and we have to calculate the heat released by the substance in aligning its dipole along the new direction of the field. It implies that here we have to calculate the work done to align this dipole with new direction of the field. So initial potential energy, that is minus Pe cos theta. Okay. Now initially, now these particular molecules are polarized, means are aligned with the electric field. When are aligned with the electric field, It implies that net dipole moment, that is along the electric field. So angle between P and E, theta, that is 0. So P, substitute its value 6 into 10 raised to minus 6. E, that is 10 raised to 6, cos 0. So this turns to minus 6 joule initial potential energy. Now final potential energy. So final, that is minus Pe cos theta, but now theta, that is 60 degree. Angle between P and E, that is 60 degree. So if you substitute the values here, you will get U final, that is minus 3 joule. So here work done, that is change in potential energy. So change in potential energy, that is final minus initial. So that turns to 3 joule. And this must be the energy released in aligning the dipole with new direction of the electric field. Clear to all of you?